So for the last 4 sessions, we've been talking about essentially the use of logical relations for proving semantic type soundness. I want to go back to some of the motivation for logical relations that I started out with on day 1, because I think it would just make a lot more sense to us now. So what I've shown you is one style, is basically unary logical relations, and then I've added language feature after language feature after language feature. I've gotten you very, very far, all right? But I want to give you a sense of how useful these things are that you've learned about, because you can generalize them really, really easily to do a lot of different things. So we've only seen, unary logical relations for type soundness. And some of you may be thinking, oh, okay, why do I need to do all of this complicated stuff? If I just wanted to prove type soundness from mutable references, I could just use progress and preservation. And you'd be absolutely right. If you don't need to do anything else funky, like, like the example I gave you with, if you have unsafe Rust code that you cannot type check, but you want to be able to make sure that it is sound sort of at the at the borders, at the edges, once you're done running it. You can't type check the code itself, but you can show that it's semantically well behaved with respect to certain Rust types. So that kind of thing, semantic type soundness is very good for. And actually, on that vein, someone came up to me after I had said that, I think on day 1, and said that even in the simply typed lambda calculus, you could have something like, if true, then 5, else false, right? We can't type check this in simply typed lambda calculus because one branch is returning an integer, the other one is returning a Boolean, but this is semantically type safe. True, it's always going to take us, this thing is always going to belong to E of int. So that's a very, very trivial example of something you can do, right? Even if you can't syntactically type check it, it's semantically well behaved. Okay, now what I'd like to sort of leave you with is, even though I've shown you unary techniques for proving type soundness, the real value of logical relations often comes up when they are binaries, okay? So we set up logical relations not like V of tau is inhabited by a single value such that something. We start talking about pairs of values, V1, V2. And we start talking about pairs of expressions, E1, E2. And what we can set them up in so many different ways for so many different purposes, but let me just start with the most simple, generic use of these. You can set up a logical relation for proving equivalence of programs. That kind of thing is extremely important for proving the correctness of program transformations that you might be doing. You can think of them as compiler IRs, compiler optimizations that are doing rewrites within the same language, assuming both of your terms are coming from the same language. And every single thing that I've shown you, I've scaled it all the way from simply typed lambda calculus terms to recursive types and then to mutable references. Going from those to the binary versions of those involves very, very tiny amounts of subtlety. I have talked about those kinds of things in prior years at OPLSS, so you're welcome to go look up, watch those videos. And but you kind of grasp the most important hard parts of what you need to do. Turning them binary usually means something like, if I run E1 and it reaches some irreducible state, then when I run E2, there will exist a V2 such that E2 also reaches an irreducible state, and then the V1 and the V2 will be related in the V relation at type tau. Basically, that's what happens, okay? Logical relations are really, really important because often we need to prove contextual equivalence of program fragments. Often we write this as under gamma. Suppose I have an E1 that type checks and has type tau, and then I have a separate E2 that type checks and also have type tau. And in my big program, I want to replace the use of E1 with perhaps a more efficient E2. Okay? What I need to show that, in order to show that that's okay to do, is something called contextual equivalence. E1 is contextually equivalent to E2 at the type tau. The definition of contextual equivalence, I should have written this up here, basically says that for all context C that have a whole that is willing to accept terms of type tau, which may have open variables from this gamma, given that maybe I have a closed program that has some other result type tau prime. So given any context that has a whole of the right shape, a whole that accepts the C1 and E2, if I stick E1 into the hole and it terminates, let's say terminates with a certain value, but we don't necessarily need to write that in a non-terminating language, then C with E2 will also terminate. If you can prove that, that is called contextual equivalence. That means that in any bigger program, you are allowed to replace E1 with E2. Generally, proofs of contextual equivalence are really difficult to do directly. The reason for this is that one context that we have to consider, you have to think about all possible program contexts. And a program context is, you can put a hole in that program anywhere at all, and it is a program context. But one possible program context looks kind of like, you know, under the lambda, you have more context, or you have somewhere in here, you have the hole. These kind of contexts, which are under a lambda, are tough to think about, and they're tough to just sort of inductive. That's what makes it difficult to do proofs of two terms being contextually equivalent directly by induction on contexts. So instead, this is a very established proof method. Instead, you set up a binary logical relation, okay? And you prove, so now my tilde, my whatever equivalence symbol is going to not be contextual equivalence, it's going to be a logical relation. You set one of these up. Under the hood, it is simply referring to an E relation that talks about closed terms being equivalent. Okay? I mean, you set this up literally by generalizing what we were doing. You say for all gamma 1 and gamma 2, as in give me two substitutions for my two programs that both belong to G of gamma, I'm going to go ahead and close E1 with gamma 1. I'm going to close E2 with gamma 2. And then these two terms better be related in my binary E relation. See how natural it is? It's exactly what we've been doing. We just make everything binary. So it's, what I'm trying to show you is that it's a really trivial extension, but now suddenly you start defining, using the techniques that you already know, you start defining binary logical relations that can be used to prove equivalence of, contextual equivalence of programs. Generally, there are technicalities. You have to show that the logical relation is sound for contextual equivalence, meaning that if two things are in the relation, that they are, in fact, contextually equivalent. I've covered all of these things in the context of all the features that I showed you, but also for languages with polymorphism in prior years. So if you want to learn about polymorphism and parametricity and how to prove free theorems from types, you know, I'll refer you to, like, I think last year, my last two lectures were about parametricity and polymorphism. Okay? And there are prior year lectures as well. So that's just to say that, like, you know, the real benefit, you can't do proofs of program equivalence using progress and preservation, right? This is when you really start to need this stronger proof method. So what you've learned is really the foundation of that. And then these binary logical relations are not just useful for equivalence of programs in the same language. I said this on day one, but like, let's repeat it now that you've seen everything. You can set up binary logical relations between programs that come from two different languages as well. I can set this up so that the first E is an expression in my source language, and the second E is an expression in my target language if S and T are the source and target language of my compiler. People have used logical relations like this to establish semantics preservation or correctness of a compiler. Okay? So those are program transformations that are going from a high-level language to a low-level language. And once you write down the logical relation, you treat it as a specification of when programs in the high level are equivalent to the programs in the low-level language. And then what you do is you have to, your job then is to show that when your compiler takes an arbitrary source term, let's say well-typed source term, and compiles it, ES, let's say, and compiles it to an ET, you have to show that for any ES, if your compiler produces an ET, then ES and ET are related in the logical relation. That means that however this one behaves, this one will behave in an equivalent manner. Okay? That's the essence of the idea. So it starts to generalize in very, very powerful ways. What else do I want to say about this? You can use them to prove binary logical relations can be used to prove type soundness, or rather a security property called non-interference for security typed languages. That's a binary property as well. So there are just a vast number of uses. Any questions? I'm going to show you yet another use today of unary logical relations that look different from the ones we've been talking about. Yes, Nico.
I have a question.
Yeah.
Maybe I missed something, but when you showed that ES was equivalent to ET, or you wrote this formula,
yeah.
which I think says expressions will be sort of well-typed. They won't go wrong. If you
Yes.
That doesn't say that they do the same thing, right? Just that they both don't go wrong.
No, so when we set up, I haven't actually shown you how to set up the binary ones for a source and target. But if I were to do an example, by the way, if you want to see an example, lectures from 2016. I did compilation that year. You set it up, let's see, can I do this on the fly? Do you want to see an example? Roughly speaking, you can do, okay, let's do something very, very trivial. Maybe I have Booleans in my source language. So I'm setting up a ST logical relation that relates source terms to target terms. I'm going to index it by types of the source. So bool is from my source. Okay, but I'm going to compile my Booleans to numbers. Okay, so how would I set up this case of the logical relation? I would say true is related to, let's say, 1. Actually, let's make it, yeah, okay. True is related to 1. Okay, and false is related to, maybe I'll say any number that is, maybe I'll make it any positive number, or any number that's not equal to 1. In other words, I'm okay with compiling true to 1 and false to, I'll probably do 0, but I'm just setting up my logical relation so that it treats any non-1 number as that. In fact, let's just make this 0, because I have an example later that I want to show you. So I'm doing a funny thing. I'm compiling my trues to 0 and my falses to non-0. But whatever. I get to decide, right? It's my compiler. And I just have to. You can do it differently. But that's actually another indication of the fact that we make choices, right, when we compile. We can do things in the conventional way, which is what I wrote down before, or the slightly unconventional way. Things might, or you could have set this up so that true is 1 and false is 0. That might have certain implications for how you interact with something that is, morally speaking, a Boolean when it was compiled, right? Do you really want to make sure that when you do the equivalent of an if-then-else, right, at your target level, do you really need your false to be only 1 number, or are you okay with anything that's non-true, right? If true is 0, then anything that's not 0 should be treated as false. These are decisions, right, that you have to make about your target and what you're doing there. Okay, so I don't know, Nico, if this answers your entire question, but here's an instance. If I were to do this for, let's say my compiler path was something like closure conversion. This I don't know if I completely will do on the fly without messing it up, but morally speaking, what would happen is you would say that a lambda in the source language, it's a lambda int or int, so let's say x is an int, and something is related to something that has the shape of a closure on the target side. So I would say a lambda on the source side is related to, I'm assuming my target language looks different. Normally I write them in different colors. That's why I have slides today, because I want to show you target languages. It would be a pair of some code, and so basically the function and an environment, because these, this function might have free variables. So I'm just going to say code, environment. And then you have to have conditions on, when these two are related. But essentially what this definition would say, if you give me a value v that belongs, a value v on the source side that is related to some value vs vt, right? Value on the source side that's related to some value on the target side at the type v int, which is the source type, then what will happen is vs will get plugged into the body, and when I run, I expect to get an int. But the vt is interesting. What the vt will have to do is you will have to take the target value, you will have to go ahead and take everything in the environment along with the target value and substitute it into the code, because that code, after closure conversion, expects both the environment as an input, but also an argument as an input. So what you will write here is, roughly speaking, that if I take my code and I apply it to the environment, comma, vt, then this is related to E with vs for x on the source side. Sorry, I'm really making this up as I go, at the result type, which for us is int. What did I do? I basically did the logical thing on the source side, and I did the other logical thing on the target side. I just know what my representation is. I'm saying, give me two inputs that are related at this type. I need to do application on the source side, which looks like normal substitution, and I need to do application on the target side, which looks a little different, right? Code expects this particular environment as input along with the argument VT. So you do this kind of game. Is that good? Okay. So you set this up, then you know, the whole logical relation becomes your specification of equivalence. And there you have to be a little bit careful. I am specifying it, so I'm trusting it.
That's what I was about to say.
Yes.
You then would want to show that this makes some sense. I guess.
Yes, exactly. Then you prove the fundamental property in you, which is basically that the compiler satisfies. Yes. Oh, yes. Okay. I'll repeat questions. Sorry, I always forget. Yeah. Question?
Were you asking me or
now I'm asking you.
Okay.
Yeah.
Just a minor question, but in your example definition of a binary relation for something along the equivalence, why do you have separate context gamma 1 and gamma 2? Like, couldn't you, if you, let's say you had something that we wanted, some ES and ET that we wanted to show, you know, because they were close enough.
Yeah.
Couldn't you just have the gamma 1 and gamma 2 that were different enough that this definition would not hold, or this relation would not hold for them?
Okay, so the question is, why do I have a gamma 1 and gamma 2?
Instead of just a single gamma view.
Instead of a single gamma. Okay, if I am working, if both the expressions on the two sides in my logical relation are coming from the same language, then I might have some hope of using a single gamma, but even that is not general enough for a lot of the free theorems that you might, for a lot of theorems that you want to prove, for instance, in the presence of polymorphism. Often you want to prove that I have a polymorphic function if I apply it to a type, something, let's say for all alpha, alpha, or alpha, that type, right? Let's say I want to instantiate that with a type int on one side and the type Boolean on the other. That means that the inputs that I'm going to give the functions now have to be int on one side and Boolean on the other, right? So I do need two separate substitutions coming in for the two different programs.
But would you need to prove that in somehow, there's some way, there's some other way?
They're related?
Yeah.
Okay, okay, and now I see. So let's go back to this instance of I have source on one side, target on the other. When I pick my substitutions, my gamma 1 is actually a gamma S, and my gamma 2 is actually a gamma T. So I'm saying, give me a whole bunch of source, syntactically source values to substitute for my variables on this side. And wherever the variables were in the source program, in the target program, there's somehow those variables. Maybe you represented them as De Broglie indices. I don't care, right? We'll take care of that kind of administrative detail separately. But basically, give me the corresponding inputs for those corresponding holes in the target program. And what I'm really saying here, I should have put parens, is that these two are related in G of gamma. So there, in the G of gamma definition, where we used to say V belongs to V tau, we're immediately going to change that to the VSs and VTs are related in the V tau. Okay, so you're scaling that up pointwise, yes. Sorry, I wasn't precise about that. Yes?
Suppose you wanted to start step indexing and looking at like the closure conversion step.
Yes.
In the past, when we were doing the unpack and pack in the step indexing, we started decrementing, but now it looks like we'll have to unpack one entry but leave the other one the same. So how do we know to do step indexing now with the two entries?
How do we know how to do step indexing when we have two programs? So this is something that I banged my head against when I was a postdoc. I really banged my head against it for many, many months. The funny thing about step indexing when you go from unary to binary is that the step only affects one side. You don't count steps on the other side. You allow an arbitrary number of steps on the other side, which basically means that you end up setting up logical relations which are saying, if I run the thing on this side and it terminates, then that one will also terminate. So they're really approximation relations, and if you want the equivalence, you want equivalence in both directions, you say, again, I'm going to go back to 1 and 2 now. 1 and 2, assuming they're in the same language. If you want the equivalence relation, then you say E1 is equivalent to E2 if E1 approximates E2 and E2 approximates, flip the directions. You need to say both, and a conjunction of both directions. Okay? Okay, so that said, let me just show you what we have to do. I'll just show it to you for recursive types, not for mutable references. You basically say E1 is related to E2 for k steps if for all E1 prime, and normally when we do binary relations, we already construct them assuming that they're well-typed. You know, when we were proving type soundness, I couldn't assume that they were well-typed in the logical relation, because I was trying to prove that property. But here, when we set up binary relations, we're perfectly okay adding an assumption everywhere. I won't write it down, but I'm telling you that I'm assuming it. E1 is well-typed at type tau, and E2 is well-typed at type tau. Even at the top level, I'm assuming this is well-typed under gamma and has type tau, and so does this one. Okay, so I'm building the relation out of terms for which I know I'm well-typed. Or at least that's one strategy that works out quite well. Okay, so E1 is related to E2. You basically say, for all E1 prime, such that, and for all j less than k, which is what we were doing yesterday, if E1 reduces to E1 prime in j steps, and here I'm not going to say irreducible. I'm just going to say value, because I'm assuming that they're well-typed. Okay? Tiny distinction, but they're well-typed. Okay, so, or you can say irreducible. It basically amounts to the same thing. Then there exists an E. In fact, I won't even write E2 prime because I know it's going to be a value. There exists a V2. Why don't I just write this as V2? Make my life easier. Okay, so for all V1, such that E1 reduces to V1 in j steps, better, then there exists a V2 such that E2, so this guy terminated, E2 will also terminate, but we don't care in how many steps. We really don't care. It could be fewer than k, could be more than k. Reduces to V2. And V1 and V2 are going to be related in the V relation for the remaining number of steps, which is k minus j. I can't tell you how many formulations of this stupid E relation I played with back in 2006, 2005, 2006, putting the step here, there, J1, J2, all sorts of things, until finally, like, you know, it kind of dawned on me, and, you know, then I could explain it to the rest of the world that really it's a step index in the sense that it's giving us an induction metric. So don't take it too literally as a step index. It's not bounding both sides. I had a formulation where I was trying to keep the k as an upper bound for both sides. But ultimately what that means is as you lower that k, you go down to 1. You're insisting that both programs take the same number of steps. It's a completely useless logical relation. It's not going to give you contextual equivalence in the arbitrary sense, because contextual equivalence doesn't care about how many steps you take. If you wanted a contextual equivalence that was sensitive to the number of steps both the programs are taking, then it might work. But that one doesn't, you know, it doesn't help you with general contextual equivalence. Yeah?
You said a bit earlier that the types don't matter anymore because you're assuming that your terms are one type.
Yeah.
So could you, instead of indexing by the type, you could just index by the terms of the source language?
Instead of indexing by the types, I could index by the terms. I'm going to go back to the premise of your question where you said the types don't matter anymore because they are well typed. I didn't quite say that. What I wanted to say is that I am just going to assume that E1 reduces to a proper value because I know it's well typed, instead of trying to say, oh, it reduces to something, and now I have to show that it's not stuck. Because I've assumed type safety, I kind of know that the terms I'm building my relation with will never get stuck. So I sort of, you know, give myself that property and then go start trying to prove programming equivalence. Does that make sense?
Yeah.
So I quibbled with the premise of your question and didn't quite answer the question. But maybe there's something to be said about your question, something about indexing, not indexing with types. Let me make the following observation. I have only shown you logical relations that are indexed by types. And for years, people used to think that a logical relation, by definition, that phrase had to mean that it will be indexed by types and can only be defined for typed languages. That is not true. Now that we have step-indexed logical relations, you can set up logical relations for completely untyped languages because you have an induction metric, the k. I can erase all the taus in the logical relation logical relations that we've been defining, and instead give you a logical relation that looks like, that doesn't have v's indexed by separate k's, indexed by separate types. Instead, it simply has a V relation. No, sorry, nothing there. Nothing there is the point. Indexed by K, and in it, I will put, let's say, true. I'll just stick to the binary one. Sorry, the unary one that we were doing. Union, all lambdas, lambda x dot e, untyped, such that for all v drawn from values that are good for, here I have to go down. No types, but I had to go down here. I'm defining vk. I can't use vk. Remember in the function definition, I was allowing a j less than k because I said, oh, over here for the function type, I have tau 1 or tau 2, and here I only use a tau 1, and here I only use a tau 2. Now that my types are gone, I don't have them available as an induction metric anymore. Instead, I'm only just going to do induction using the step indices. And this is basically how you can set up a logical relation for the untyped lambda calculus, or any untyped language. You just define it as a big union of something. I can throw in some pairs, if you like. You know, the pair of v1, v1 prime is related to the pair of v2, v2 prime. If v1 is related to v2 in v k minus 1, and v1 prime is related to v2 prime in v of k minus 1. See, it's completely untyped. Just keep going. Just leave the types out and make sure that you're going, the step count is going down so that you can look at it, and by inspection, you know that it's well-founded. So this is a kind of novel thing. I think the first time we used this was probably, there's a Popple 08 paper on imperative self-adjusting computation, of all things. Yeah.
So are there any cases where just the languages are too dissimilar that they won't work with this?
I'm going to say no. Because we have been doing it for source languages and target languages. And there's even a paper by Derek Dreyer and Gil Her, probably Popple 10-ish, 10 or 11, Popple 2010 or 2011, where they have ML and assembly. That's about as far as you can get, right? And you can do it. It requires some patience, because when you're doing assembly on this side, you're like, okay, what's going on? I have to be really, really careful with my proofs, because low-level languages are so tedious, right? But it's tedium. It's not impossibility. Yeah. Oh, the question was, is it that we can't set up logical relations if the languages are too far apart? And the answer was, well, people have done even ML and assembly. Usually, if you're trying to do this for a compiler, you kind of want to do it pass by pass. You would like some notion of transitivity, perhaps, so that you're not doing ML all the way to assembly. Compilers are written pass by pass, so we'd like to. So some of these things are still open problems, though. If you want to see, we have a paper called The Next 700 Compiler Correctness Theorems. If you're interested, it talks about various ways of that people had been doing compiler correctness proofs using different proof methods, and how they have different limitations when it comes to kind of doing what we call vertical compositionality in a compiler, which is pass by pass. You want to prove one pass correct, another pass correct, and it should imply end-to-end correctness. That's vertical compositionality in a compiler. And horizontal compositionality if at the same time you want to allow linking with arbitrary code. What code do you allow linking with? Only code that comes from your compiler, or code that might come from any other arbitrary source language? These are really hard problems, ones that I still don't think we've answered perfectly. Yes?
Sort of like a quick question. Could these be threads like, do you know if like Concert uses logical relation?
No, Concert does not use logical relation. So that's an excellent question. Concert basically does a simulation proof. It shows, it's showing that as you take steps in the source, you're taking corresponding steps at the target. So there is further terminology, which is forward simulations and backward simulations. I could get into a lot of detail, but CompCert's beauty is that it eventually needs a proof of backward simulation, but it ends up sufficient to do a forward simulation. Anyway, lots of technical detail there. But CompCert is not using simulation. Is not using logical relations. The very first CompCert proof, and for years people did not realize this, was a proof only about whole program compiler correctness. Technically speaking, that theorem did not let you link with anything at all, which is bad, right? Because we always link with low-level libraries. So that's where this conversation sort of started. How do we prove correctness of compilers that allow linking? This kind of strategy, where I'm setting up something between source and target, if this was back to source and target, S and T, it lets you say that it gives you a free environment, right? That's where you can stick in the things that you link with. But unfortunately, I call these cross-language logical relations between source and target. But the problem is that if I have code, source, and target, and it's proved correct because my compiler compiled it, now I want to link it with some target code that came from a different language. I can only do it according to this definition if you give me a gamma S and a gamma T. So if I put this into gamma T, I still need to give its corresponding gamma S. That means I can only link with code that is related to some source program in my language. So that is its limitation. That's a pretty big limitation. We can't link with arbitrary code that was compiled from some other language. It has to somehow be related to code in our language. That is what this paper, ICFP 2019, the next 700 compiler correctness theorems, that is what that paper is about. Yeah?
There's a later paper about connection between UC simulation and robust calculation as a notion of compiler correctness.
Sorry, say that again. Is there a later paper? Is that what you're asking?
Yeah, there is a paper about that. Do you know if there's any connection between proving compiler correctness using this and UC simulation or
UC simulation?
Yes.
I don't know what you're talking about. What is UC simulation?
Yeah, there is a recent paper about they define a compiler correctness as a robust type of property.
Oh, that paper. Okay, yes. Let's take that offline because it's not paged in enough for. Oh, more questions. I really want to show you something else cool. Critical questions? Yes. Yes.
You mentioned logical relations for not interfering properly.
Mhm.
Do you have other references?
Oh, there are so many. You can look at some of Steve Danswick's papers. I think his PhD dissertation has one, but there are many follow-ups. Like so many papers on security type languages make use of logical relations to prove soundness, to prove non-interference. I can ping me on Slack or something, or post in the channel. I can find you some. Yeah. Okay. Oh, that question was about, are there references to papers that make use of logical relations to prove non-interference? Yes?
Suppose we have two different languages and you want to do logical relations together. And the higher level language does not have the notion of memories, but the lower level does. Does that mean when you do them together, you have to extend the higher level language to also take care of stores or memories so that you can talk about them at the same time?
I have done, so what you're describing sounds like a lot of work that I've done on setting up multi-languages, where you take two languages. In this case, in my work, I was actually doing languages which were the source language of a compiler and the target language of a compiler, and I put them together in a multi-language. In fact, maybe I should start on my slides. Yeah, let's start on my slides, and maybe I can find the right moment somewhere in there to answer. And but Marco has his hand up.
Yeah, I also have a question.
Yeah.
Is it a good question to ask? I have a language A and language B. I build the logical relation. Or is it the right question? Or we should think about what we want to prove first?
I think we should think about what we want. If we have a language A and a language B, what is it that you want? Do you want language A and B to be two source languages that are interoperating? And then what do you want to prove about that interoperation? That's a very important question. Or do you have languages A and B, are they the source and target of a compiler? And you want to prove something about that, right? You want to prove straightforward compiler correctness that only allows you to link with code that came from your source, right? Then you can do these. But there are other things you could do. You could
Maybe a situation where logical relations are not the good tool.
might not be the good tool, or your languages might have such similarity that you might have a much better, easier proof method that you could use. Right? If they're not, often logical relations are a better tool when things are more different from each other. But they're not necessarily, they may be too complex a tool if your languages are super close, in which case you can show some sort of simulation argument because they're kind of stepping roughly in lockstep anyway. Okay? Not exactly lockstep, but kind of. They're not doing things that are crazy different from each other or in the completely different orders. In that case, using some sort of simulation argument is a much easier trick. Okay? All right, so let's go into language interoperability. I want to show you a use of unary logical relations. Okay, so this is like, there are many, many different languages in the world. I like to show this slide when I start talking about language interoperability. But I want to talk about type soundness, right? Because that's what we've been talking about. So in theory, for all of these different languages that we have out there, ML, Haskell, Java type, what do? People in our community, right? Someone takes a kind of core of the language, the core of ML, the core of Haskell, the core of Java, all right? Maybe a featherweight Java, and goes ahead and does a type soundness proof. Often they're done using progress and preservation, right? But you prove at least that the core of the language satisfies type soundness, okay? But the problem that we as a community usually ignore is what happens when you go off and implement this language. Is the core a valid core for which you've shown type soundness? Does it imply that the language as implemented is still type sound? And I would say that in practice there is a problem, which is that every single language, when you go off and implement it, you have to provide it with a foreign function interface because code from your language will have to link at least with code written in, C libraries. At the very least, C libraries, right? If you're ambitious, you'll allow interoperation with other languages as well, but you can't even get off the ground if you're not going to implement an FFI that lets your language connect to C, right? Okay, so at that point, what do we do? Well, Camel, GHC, Java. At that point, you basically build in some kind of FFI, but in essence, that FFI, the foreign function interface, is an escape hatch. It's allowing you to escape the rules of the type system, right? In some sense, unsafe code sitting in the middle of Rust is allowing you to escape the rules of the type system, right? You hope that it's correct. You hope that anything you're linking with using these escape hatches is correct, but you don't know that it is, right? Correct or safe, type safe, but you don't know that it is. You don't know how it is affecting the type safety of the rest of the program that you are writing, because those are not interactions that anyone considered when they were doing the type soundness proof or the progress and preservation proof. So the question is, for people who want to prove the soundness of languages as they're actually implemented, what techniques can we use, to show that not just the core language itself, but the language as it interoperates with something else, that is actually type sound. In other words, how do we ensure the type soundness of a foreign function interface? Are there proof methods for doing that? And what I want to show you is that you've been learning about one. If you tweak what we've been doing for the last 4 lectures, we'll get there. Okay, but let me just say, okay, I've already sort of made this point. There are many different languages, and they have many different forms of interop. And these are the kinds of FFIs that we don't even have proof methods, really, to address this question of, how would we prove them sound. I want to talk about the one attempt many years ago that was made to address language interoperability in a more formal way. Usually it's such a messy question that we run away from it. If you look, there isn't that much work on language interop, at least not until very recently. Okay, so back in 2007, Jacob Matthews and Robbie Findler wrote this really nice paper. It was called Multi-Language Semantics. It was on multi-language semantics. I don't remember the exact title. But basically, it had this idea in it. If you have a language A, my red language, and you have a language B, my blue language, then take all of the terms of those languages, those are the ... dots, and then add 2 new syntactic forms. We call them boundaries. The boundary AB with blue language term underneath it allows you to take blue language terms, language B terms, and put them in A language context. So I want you to read that as, if I took a blue E of blue type tau and stuck it under this boundary, I'm going to give you some typing rules. Then the red language can assume that it's getting something of type red tau. Okay? And vice versa. So it allows you to embed terms from one language into contexts of the other language. So I can write a little blob of blue code and then put it in a program which is all red code. Or maybe that red program can have other blue blobs in other places. Maybe my blue program can have some red program inside it as well. Okay? It allows for all of that. Okay, so we give typing rules for the boundary terms that basically capture what I just said to you, that if the blue term has blue type tau, then the red context is assuming it's getting something of red type tau, and vice versa. And then the interesting work happens when you define the reduction semantics for the boundaries, okay, when you define the operational semantics. So how do we run a term, a boundary term that looks like this? Well, you take your blue term, and you run it exactly using the normal, standard operational semantics of the blue language, and you keep running it until you get that blue language thing, expression, reduced to a value form, and then you do the interesting work. The interesting work of how do I convert a blue value of this type to a red value that has this type, okay? So for example, if maybe I'm representing integers as binary. So if this was 101, I need to convert it to the number 5. Just to take a trivial example. But more importantly, if these are functions, you can end up, if this is a function in the blue language of some type tau1 arrow tau2, then you can convert it to a function in the red language of some type, let's say tau1 prime to tau2 prime, by basically saying, oh, I need to produce a function. I don't have this in a slide, do I? I wasn't going to show it. I'll show it though. Basically, for anyone who's familiar with contracts or higher order contracts, the idea should already be clear. So if I have a lambda x dot e in my of type tau1 arrow tau2, and I'm writing my AB boundary and I want to convert it to the other language. So this is blue and this is red. I wish I had colors. Okay, tau1 prime to tau2 prime. What I'm going to do, these are B language terms, right? What I'm going to do is turn it into a red language lambda that takes a tau1 prime. Sorry, this is blue. I need colors. Are there colors?
I think one of the boxes at the end of the thing
Has a color? Ah, yes, indeed. Thank you. I don't know if you'll be able to read the colors. That's the other problem. Okay, white is the outer language, A, and I'll use blue for what is actually blue. So I'm not going to use red. Okay? All right. So we're turning good? All right. We're turning that into this. So I want to produce this A language tau1 prime arrow tau2 prime. So A language term that takes this, it's going to take. Oh, okay. Blue. Thanks. Yeah. All right. So what can we do? At the end of the day, we want to use our blue language function, lambda x dot e, and apply it to some input. But I'm getting my input as tau1 prime. So what I'm going to do is I'm going to convert using my boundary in the other direction. This is why I don't like switching between colors on the board. It is hard. Okay. Take the x, which is of type tau1 prime, convert it to the B language, where it will have type tau1. Feed it into the function, which wants a tau1. Out comes something that has type tau2. Convert the result from tau2 back tau2 to tau2 prime. That thing has the right type. So what did we do? We implemented a function, we implemented a conversion from blue language function types to white language function types by doing a sort of back and forth conversion. We basically took our function and put it inside a function of the other language. We wrapped it. Okay? This is also the idea of higher order contracts, but that's the basic essence, and you can implement these kinds of rules to do a multi-language semantics. Yes?
Maybe a bit of a silly question. Isn't this essentially what FFIs are?
In a sense. But I have a point. I'm only on like slide 3. Okay, so let's, do I want to, can you hold questions? Okay. All right. Okay, but this idea was nice because then you have a single language and you can use standard progress and preservation to prove the soundness. Okay, but the point that I want to make today is even though this was a beautiful idea and there's so much follow-up work, this is a tiny, tiny fragment of it. All of these papers use multi-language semantics, and there are so many more. You can just look at the citation count of the Matthews-Findler paper. And by the way, it's one of my favorite papers. And Robbie Findler is a very dear friend. But the technique does not work for how FFIs are implemented in practice, and that's what I want to talk about, all right? Let's talk about how FFIs are roughly at a 30,000-foot level implemented in practice. You normally have code coming from 2 different languages, my blue language and my orange language. They're getting compiled down to some kind of target. And that is the level at which the FFI implementer will normally go and write some glue code, some conversion functions that will convert the code that's coming from one language that's of a certain type, let's say the tau1 arrow tau2 that's blue, and convert it to a tau1 prime arrow tau2 prime that's orange, only if the tau1s and tau2s, the tau1 primes and tau2 primes themselves make sense to convert, right? You don't ever want to convert a function to an integer in the other language, right? So you as an FFI designer make some decisions about what are the needed conversions. So what we need is, for FFIs that are implemented like this, what's a good technique? What's a good proof method for proving that the glue code that you're implementing will in fact convert the code of a type tau1 into the right kind of tau1 prime so that it actually behaves like a tau1 prime in the other language, right? The type that you wanted. Like, what's the soundness of that for that glue code that gives you soundness of language interoperability at the end of the day? Okay, so I want to talk about interoperability soundness via semantic. We've been calling them semantic intermediate representations, but they're really just going to be logical relations. And here's the recipe I want to give you. If you have some term of type tau A in language A, and you have another term of type tau B in language B, normally when you go and design a foreign function interface, you're going to make some decisions about which types are convertible to which types. So let's say we're going to add some boundary terms. You're going to add something to allow people to glue things together, right? To use terms from one language of a certain type in the other language. The main decision you're going to make is basically this one, that if I allow something of tau B to appear in a tau A, in the other language, then what type should it have? And you will make some decisions about which types from the 2 language are interconvertible. This is where your decision about, oh, I can't put an int here and some function type here comes into play. You'll never add that as a convertibility rule, right? So you need to decide what your convertibility rules are, and then you'll kind of have this. So you specify these convertibility rules, and then for every single convertibility, like let's say this function type is allowed to be converted to this kind of, I don't know, code closure type or something, right? Or you might have a sum type that's converted to an array type in the other language. It could be a decent decision. So you make those decisions, but then what you have to do is you have to implement the glue code at the target level. I'm going to write these as conversion functions that take the blue tau code. If you wrap it with if you wrap some code that actually used to have blue type tau, you should be getting something that has orange type tau, and vice versa. So you implement conversions for glue for glue code basically at your target level, and that target level code is all going to be in that black colored target language. Okay. Now I'm going to tell you how we can prove soundness. You define a logical relation. You define a logical relation for both of your languages. I'm going to say that, but it's a different logical relation than the ones we've been doing. I've been showing you logical relations that come, let's say, from my logical relation for my blue language is inhabited by terms from my blue language. That's what we've seen all week, right? Instead, now I'm asking you to set up a logical relation for the blue language that is indexed by the blue types, but is inhabited by these black-colored target language terms. Similarly, for the orange language, they are also inhabited by target language terms. Basically, we're saying at the target language level, tell me what code behaves like what the high-level type wanted. Okay? Once you can do that, right, logical relation indexed by source types, inhabited by target terms. Once you can do that, you have the means. Oh, I'm not staged right. Let me just point out one thing, yes. If I'm giving a logical relation for all the types of my orange language, same thing can be said for blue, what I'm actually doing by specifying that logical relation is carving out a space in my target, a space of well-behaved terms that will behave well according to the orange language's types. There's a lot of junk in the target that will never behave like orange language types. It's outside that dotted line, okay? But what the logical relation is allowing us to do is it's allowing us to focus attention on the well-behaved one. And that inner circle you can think of as kind of a semantic IR or well-behaved semantic IR. Okay, so let's go back. What's the recipe? Once you have the logical relation, here's what you need to prove. For every single convertibility rule in your language, if any blue tau is convertible to an orange tau and vice versa, you made that decision as a designer. Here's what you need to prove. You need to prove that given any target code that inhabits the blue type tau, if I wrap the conversion function I implemented in the target language, right, that converts this particular blue type to this particular orange type, if I wrap it around this code, the code that behaves like blue type, I wrap it with my conversion wrapper, I will get some target term that behaves like the orange type. And vice versa, other direction. Semantically, what are you proving? You're proving exactly what you want. I took something that behaves like the blue type, I wrapped my wrapper around it, and I got something that behaves like the orange type, and vice versa. So it's a semantic type soundness technique that then gives you the ability to show the soundness of the glue code that you implemented, that it's actually going to take these kinds of behaviors and turn them into the appropriate kinds of behaviors for the other language. And then once you're done with that, the rest is just standard, like we lift, you can think of this as the E relation. These are E relations that we've been constructing for expressions. And you lift it up to the top level, doing exactly the kind of trick we've been doing. You get some substitutions, you close off the values, and then you say you get something. So basically, then once you prove the fundamental property, well, in order to prove the fundamental property of the whole language together with its FFI, you have to prove this lemma first, right? Which is giving you the soundness of interop. Yes?
But how do we know that the C functions are like converting the values correct?
How do we know that the C functions are?
Like, if they're like doing the right thing. Like here we only know they're.
We only know, okay, so right now, the framework that I'm showing you is not about correctness that they're doing the right thing, but it is about type soundness. So the lemma that I'm interested in, remember a little while ago Marco said, what are we interested in proving and what are we setting up a logical relation for, right? Here I'm setting up a logical relation or showing you a proof technique that will allow you to show that all the glue code, I'm not showing that it's taking something from the blue language and converting it to an equivalent term, but I am showing you that it's converting it to something that behaves like the type tau. So it's a type soundness result. Conversion wrappers are type sound. I don't know if they're correct. Maybe there's a bug. Maybe it converts a 5 to a, or maybe it converts a 4 to a 101. Right? It might, but it's at least going to convert it to things that behave like the type. And that's a good question. You know, correctness is sort of a next step. I think this framework can easily be generalized to do that, but I won't get into that. Okay, so if you were interested in finding out more about this, we had a PLDI paper about this, Semantic Soundness for Language Interoperability. That's just about this technique a couple of years ago, if you want to go wade into it. And I just want to, we had 3 different case studies in that paper, and I wanted in, now I was going to show you 2 of them, but now I will show you 1 of them. All right, because we're kind of running out of time. I will show you the middle one. how do we mix a language that's essentially a mini ML with an affine language, which we'll call AFI? This is kind of tricky because, you know, in an affine language, you can use any resource no more than once. A variable can't be used more than once. But suppose that I end up passing an affine resource over to my unrestricted language, over to ML. It doesn't know that it should use it only once. So how can we make sure that it will, in fact, do that? And the strategy that I'll use to do that here is kind of a simple, trivial one. You know, we basically use a form of dynamic checking. Any affine variable flows over to the ML side will be wrapped. And in that wrapper, there will be a little flag saying, has the resource been used yet or not? So in the beginning, it'll be set to false or unused. And then once we've used it, we'll set it to use. So next time ML tries to use it, we'll crash. Okay? It's not the best one. In the paper, we actually have a better case study that doesn't do dynamic checks for everything. It only does dynamic checks for the variables that do flow over to the other side. But anyway, that's a refinement of the thing. Okay. So I think you've seen languages, but I really wanted to step through the case study and just show you all the things that one specifies and does. By the time I get to the logical relation, you will find it easy, I think, given what we have done in the last 2 lectures. Okay? And like that's the beauty of it, that you can just sort of, what we were doing yesterday is so close to what I want to show you for this case study at least. Okay, so my mini ML just has unit, int, pairs, sums, functions, polymorphism, references. I didn't even show you polymorphism, but it won't matter too much for this talk. My affine language has lolly, right? So affine functions, unrestricted types, and lazy and additive and multiplicative pairs. Frank has been talking about these, so you understand how they basically work, right? The interesting thing to say here is, as far as judgments go, the delta has my polymorphic variables alpha, but I haven't talked about polymorphism, I know. Gamma is the standard thing. Here, gamma has the variables x, which I want you to think of as unrestricted. And I'm using A for the affine variables that cannot be used more than once, and I'm going to put those in omega. Okay? So, and there are boundaries right there. Okay? I've added boundary terms. I'm going to, this is a very trivial kind of, I cannot show you in a lecture, x86, you'll never understand it. So, so I'm taking my 2 languages and simply compiling them to a lambda calculus, LCVM, lambda calculus, VM, virtual machine, if you will. My students came up with that name. But it's just an untyped language, and it's meant to represent the fact that often target languages are untyped, right? So I'm compiling 2 typed languages to an untyped language. What I have in this language, it just has pairs, sums, the usual stuff, references, but I have the ability to fail. It's highlighted. I have the ability to raise errors, right? This is an untyped lambda calculus, and I'm going to basically make do with 2 kinds of errors. If I fail, I'm going to give you a type error. And once I prove my FFI sound, the type, that involves showing that a type error never occurs. Okay? A type error is the kind of thing where I take a Boolean and apply it to something. So that should never occur. But there can also be conversion errors. Those will arise if ML is trying to use an affine thing multiple times. Okay? So that is that arose because I had a dynamic check that caught an interrupt error. That's why that is there. Yeah.
Can the affine language use an ML name multiple times?
Yes. Yep. It can. Okay. Just the relevant bits of the affine language, right? Though I'm sure, given this week's lectures, you're familiar. But A has type tau if it's in omega. I've already told you the omega environment has the affine variables, the gamma has the unrestricted. Here we add the affine variable to that. And the important bit is that if we're trying to type check a program that has 2 sub-expressions, we have to take all the affine variables, split up the omega environment, and give disjoint parts of it to the 2 subderivations. That's how we make sure that we never reuse affine variables. We can use them a maximum of 1 time. Okay. Let's take a look at the compilers. All right. This is a very standard compiler. Nothing interesting is happening. I'm just sort of like, structurally recurring. Perhaps what's interesting is that when you have polymorphism and type application, I just forget about the types and convert them to a lambda, right, with no input there. And other than that, the conversion terms, the boundary terms. The boundary terms will be compiled. So I compile the orange term. The plus means the result of compilation. And then I wrap it with my wrapper, right, to get the thing of the other type. This side is more interesting. Okay, so what I want to do is I want to make sure, remember I said any affine variable, I'm going to wrap it. I'm going to wrap it in a thunk. And I'm going to put a flag in that thunk that is set to unused initially. And once the variable's been used, so let's look at thunk E. So given an E, you can think of E as an affine variable. What does thunk E do? It creates a fresh reference cell R fresh. So this is a ref. You can think of ref here as new, what I've been writing as new on the board for the last couple of days. So it's a new reference cell that I'm creating that contains the flag unused. Okay? And then what I return is basically a lambda, a thunk, which when you call it, you apply it to, let's say, unit. What is it going to do? It's going to go in and read the contents of that R fresh reference cell, right? See what the flag is set to. If the flag is not true, in other words, if it's used, then it's immediately going to report an error, fail with a conversion error. Otherwise, it's going to set it to used and then run E and give you the result. Okay? So it's protecting your resource. It will fail if it's used a second time. All right, so where do we use this? We use it, for instance, in application, E1 applied to E2. This is basically something of affine type, lolly type being applied to an input. So we're going to compile the E1, but we're going to compile the E2 and put it in a thunk before we give it to the E1. That way we make sure that whatever the E1 is, it's getting a wrapped resource that can't be used multiple times. And that's basically the idea. We're just using the same trick in other places as well. Okay? Anytime, like here, we're saying, oh, let's look at this pair and extract, we're pattern matching and getting A and A prime. So those are also now affine variables that need to be thunked before we pass them to a thing. Okay. So that's the essence of what the compiler is doing there. Now let's look at convertibility. Okay. What decisions are we going to make about what types in mini-ML are convertible to what types in AFI? So the first one is trivial. Unit is convertible to unit. I've written it in this funny style basically to indicate that these are the conversion functions that have been written in service of that convertibility rule. Okay? And I'm going to have these pair conversion functions that use the conversions for the underlying tau1 and tau2. All right? So I'm going to have something of this tensor type, the pair on the affine side, right? The multiplicative pair. And it's going to be converted to pairs on the ML side and vice versa. Let me show you the code for these conversions. For unit to unit, it's nothing. It's just the identity function. You don't do anything, right? Because the representation from both languages of unit should really just be unit. The target has it. For pairs, easy enough. Go and convert the first thing. Go and convert this. Oh, this should be tau2. Go and convert the second thing. And then, just, yeah. So, just return the E. And similarly in the other direction. So just convert the subterms. Okay. Here's the interesting one. I cannot possibly add a convertibility rule to this language, which allows me to convert a tau1 lolly tau2 from the orange language into a blue tau1 arrow tau2. Anyone want to tell me why not? Yes?
Your affine function is going to basically consume this argument, and
Yes.
it won't be available. But yeah, in the mini-ML, that's not the case.
Exactly. So in mini-ML, well, so if I have this function, or let's say, the problem is going, you can think about it as going from a blue tau1 arrow tau2 to going to a lolly type, right? The blue one might be using it in its input of type tau1 many times. So if you just try to convert it to the other side without any protection or any thunking, things are just not going to work. So basically what this type is saying when it says that the affine function tau1 lolly tau2 can be converted to only that type of function, is it's saying that the input must be thunked, right? So you're giving me a tau2, but it's wrapped in a protection wrapper, very much along the lines of the thunk that we saw before, which had type unit arrow, some tau. Okay, we can look at how this works. Let's just look at one direction. We don't have to do the whole thing. So if I'm trying to convert a tau1 lolly tau2 into that ML type, well, what do I need to do? First, I take the expression and I kind of run it. I bind it to x. All right. Now I have to return something of that type unit arrow tau1 to tau2. Okay? So I write down a function that takes an x thunk, which is going to be, roughly speaking, of type unit arrow, blue unit arrow tau1. And then I say, all right, I'm going to apply my x thunk to unit, which will give me back something of blue tau1. I convert the blue tau1 to an orange tau1, and we're calling that xconv. All right? Xconv is basically a blue tau1, sorry, orange tau1. Then what do we need to do? Then we're taking that orange tau1, thunking it again, putting it in this x-ack, right? Like this is the input, and this will now be the input to our original function, which is the orange tau1 lolly tau2. So orange tau1 lolly tau2 gets something of type orange tau2, which is what this is. And then we go ahead and convert the result. Okay? And the other direction is analogous. You can slowly read through it. But basically thunking back and forth. And yeah. Okay. So now that we have that, let's look at the logical relation. I'm going to set up a logical relation for the blue language and a logical relation for the orange language. And you're going to understand what this looks like because of what we've done this week. Okay. So this is going to be the shape of the value relations. It's going to have a world there, right? Until now, I was writing the world as k, psi, and I was putting it as a subscript on the v side. But here's just another way to write that same thing. And in fact, this notation appears in a lot of papers. So I think this also gives you a slight tweak on how to read that, right? One thing that I try to do in these lectures is I try not to stick to exactly the same notation for logical relations every day. But this time, I've sort of ended up doing that. So I'm glad I'm tweaking it at least a little. Because there's so many different ways that different papers will write this stuff. Okay, let me tell you what is in the world. Yesterday, for ML, we basically have ML, right, with references? For ML, our worlds were k psi. Okay? Today, I have k psi, exactly the kind of heap typing that we saw the last lecture. But in my world, I need one more thing. I'm keeping this set A. A is going to keep track of all the flag reference cells. You know those refreshes that we're creating and putting in the thunks? The protection references, if you will. A is going to keep track of every single one of those, and it's going to keep track of the Boolean value, used or unused, that is stored in those. Okay? And that is what my world will track. And we're going to assume that all the normal references of ML sit in the domain of psi, and all of these flag ref cells that get created, they sit in A. Okay, and they're disjoint locations. We're not going to, it doesn't make sense for them to be the same. Yeah, flag B is in the current world. Here's world extension. I can go from a current k psi A to a future j psi prime A prime if the following holds. If j is less than or equal to k, just like yesterday, if for all the locations in my current domain psi, psi prime of L is equal to psi of L to approximation j, I'm just using prettier notation than yesterday, and the third condition, which is novel to this particular application, for every single location in my current A, it better be the case that, that first of all, that location still exists in the future A. But second, if it was already true, as in if it already said used, then you cannot possibly set it to unused, right? So if you use something, then in the future world, you can't just suddenly decide it's unused, because that would break everything, right? Just another example of an invariant that you want to keep track of and say that I can only move to future worlds where this sensible thing holds, right? So, okay, once you've done that, you can start giving, you know, standard logical relation interpretations. You guys can read this, right? Completely normal. Blue int is inhabited in any world W by numbers, n, that are integers, right? Orange is inhabited by numbers n as well. The only weird thing is that these numbers are all written in black. They're not orange or blue, right? They're from my target language. They have to be whatever, however I'm representing them at the target. Pairs, V1, are represented at the target language by target language pairs V1, V2, where V1 behaves like tau1 and V2 behaves like tau2. Worlds functions exactly like yesterday. Lambda behaves like a tau1 or a tau2 in the current world. If you give me some future world W prime in which you give me an argument that behaves like a tau1, then I plug it into the body, it behaves like a tau2. Exactly what we've been doing. Right. My point here is that you can do this now. And then here's the interesting one, but even this does not require that large a tweak. Okay, so for lolly, what do we need to do? We want to say that a target language lambda, lambda x dot e, behaves like an orange tau1 lolly tau2, right? Okay, now we have to keep our implementation strategy in mind. We are thunking things, right? So what do we say? You say, if you give me any argument v, such that in any future world W prime, that is a future world of W, V behaves like an orange tau1 in that future world W prime. So far, standard, right? Then what am I going to do with that input? The thing is, I can't just plug it into the body of the function. I need to thunk it, because that's my implementation strategy. My compiler is doing that too. So this definition needs to reflect it. So what am I going to do? I'm going to construct a new world, W double prime, that is just going to take my W primes, which is my kind of current world in which you gave me the argument, all right? And I'm going to say, oh, W double prime, it's the same as W prime for the K. It's the same as W prime for the psi. Just copy that stuff. But in the A component of my W prime, I'm going to add my new flag ref cell and set it to unused, because it's unused right now, right? And then what I'm going to do is, instead of directly substituting V into the body of E for X, I am going to take my V, thunk it, which produces this new location, which is the rfresh, right? Thunk it, and then substitute the thunk into the body, and it behaves like a tau2. My point is that you can do this. If I had stopped yesterday, you could have done this, right? Because that is what's kind of happening in a lot of, like, once you understand how these logical relations work, and you figure out how it works for different features, after that you just have to, one of my students used to say, listen to the operational semantics of the language. You just have to listen to your language, all right? And you start to figure out where your definitions need to be tweaked in order to do a certain thing, right? You have to think about what invariants are preserved. Oh, okay, the flag can't be set from used to unused in the future, et cetera, things like that, right? Okay, and then finally the E relation. When does a target language expression behave like either a blue or orange tau? Here, I really have two E relations, one for the blue one and one for the orange one, but they look identical, so I've just written it as the neutral black, but this is either a blue or an orange type. Okay, so when does a target term behave like a source type? Okay, when you give me, instead of store, we wrote heap in this paper, H, all right? So those big S's yesterday are a heap here. So for all heaps that satisfy the current world, I should have had a J here. For all J's that are less than the K in the current world, if I run my heap expression pair for J steps and I get to some H prime E prime, then either that term has failed with a conversion error, because now conversion errors are possible. We can't simply say that no errors will occur. These conversion errors, it's a dynamic checking strategy, so these are possible. Or the standard thing, the rest of it is standard. There exists a future world W prime that is a valid future world of our current W, and the new H prime satisfies the W prime, and E prime is in the value relation at the time. So this is exactly what you saw yesterday, and this is the one thing we had to add, because now we have dynamic errors that are catching interrupt failures. Okay? All right. And then just to, I'm not going to show you this definition, but just to give you an idea, at the very top level, you scale this up. You close the variables just like we do before. The only funky thing here is all the affine variables in omega, before you substitute them into the body, it's not enough to just say, give me a gamma. You know, orange gamma, so to speak, or something, right? Give me inputs for the affine variables. You have to take the inputs for the affine variables that are of the right types, and then wrap them all in thunks before you substitute them in to your E. That's it. Okay? And of course, they'll all come, their thunks will have locations for the flags. So those locations need to be, set to false. They need to be added to the world, etc. Okay, and that's the recipe, right? Those are the steps. Specify your convertibility rules if you're trying to design an FFI. You implement your conversions, the glue code, and then to prove soundness, you define the logical relation, you prove conversion soundness in this way, and then you finish with the fundamental property and you get type soundness for both languages, or for the interoperability for the FFI, as well as the combination of the two languages. There's some details I've left out here. I'm writing this with only blue environments here and orange environments here, but in the paper we actually have the ability to take orange variables and stick them into blue language context. So we have to put blue context here if we want to allow blue variables to appear in there, and we have to put some orange context here if we want to allow orange variables to appear in there, but the whole thing just generalizes pretty simply. This thing that I've shown you, the sound interop has a runtime cost. You'll notice that all the affine bindings have to be checked on use, even if I never pass them to ML. In AFI, I know that an AFI code will never, ever use them more than once because it type checks. So this is a naive strategy that I've shown you. The one in the paper is actually smarter. It makes a distinction between, you can do a quick program analysis to figure out which affine variables are flowing over to the ML side, and basically your compiler can thunk only those. And the ones that are not flowing, you keep them separate. You don't put thunks or wrappers around them. That gives you a more efficient implementation. Okay? I won't go more into it. Just to mention that it exists, otherwise it looks very, very naive. Just move on. Okay, so I had another case study here, but I'm not going to talk about that. Let me just sort of conclude. I'll put these slides up if you want to look at it, but essentially this case study is from the paper, so you can see it in the paper. All right, so the state of the world is such that, this paper that we had a couple of years ago has a proof methodology that, can hopefully be used to verify FFIs, but it's really showing you 3 rather simple examples. Actually, the third one is pretty fancy. It's somewhat idealized, but it's interop between a between a language with manually managed memory, and the other one is garbage collected. That logical relation is a bit sophisticated. We had to think a little. More than a little, to do that third one. Maybe we had to think about the AFI one as well. But anyway, so the hope is that ultimately, how do you use this technique to verify the soundness of actual foreign function interfaces? One of the things that we're interested in looking at in my group is interop between ML and Rust, compiled down to WebAssembly. We've been doing a lot of interop work on top of WebAssembly recently. But essentially trying to apply this sort of a methodology to interop between these languages. And there are so many things you can do in terms of interop design. It's a question of making decisions. What Rust types can be converted to what ML types? By the way, ML and Rust interoperability is really hard, right? Because Rust has this notion of ownership. It has a notion of borrowing. If you take something that's owned or mutably borrowed and pass it over to the ML side, ML can, pretend to give it back to you, but basically keep copies and keep using it afterwards. So that immediately destroys. It's kind of analogous to the ML AFI situation, right? It's trying to use a resource that cannot be used more than once, multiple times. So it might give it back to Rust, and now Rust thinks, oh, I got my own thing back, or my mutably borrowed thing back, but ML keeps messing with it, right? You can cause programs to crash that way. So how do you rule that out? And then I want to sort of conclude with this one thing, because I think this is one of the cool ideas to have come out of this paper. So after we had written that PLDI paper, and my student Andrew Wagner is an author on that paper, but he noted several months later, he's like, Amal, oh, by the way, I didn't say realizability relations. The logical relations that I've been showing you in the slides, which are indexed by source types, but inhabited by target terms, we've been referring to them as realizability relations. This goes back to a paper by Nick Benton back around 2007 or 2009. He was not looking at interoperability at all, but he was sort of saying, when target code that actually implements or realizes the behavior of a source term, let's refer to these as realizability relations. So that's another phrase to keep in mind. You might see it in the literature. So these kinds of logical relations, which are indexed by source types and inhabited by target terms, Andrew points out, these relations, they're specifying a lot. They're specifying all the low-level data layout. They're specifying all the calling conventions. They're basically specifying an ABI. So this is a beautiful technique for specifying ABIs. Right now, if anyone, I don't know, for years people have said ABI to me, and I kind of go, oh my God, and maybe I'd stop listening. I don't know. But ABIs are basically, they're about a lot of low-level detail, but they're always only specified textually, right, in prose. Using this technique, we can start to specify ABIs using, formally, basically give formal specifications to ABIs. That opens up a lot of possibilities for verification. You can formally specify your ABI. What we'd like to do is we'd like to formally specify an ABI for Rust. Nico may or may not agree on what exactly the ABI will say, but we will see. And what I'm referring to there is the following property. I've been talking to some people, I have a DARPA program manager who's been complaining for like the last 3 years that the C ABI is incredibly impoverished, which I completely agree with, right? The C ABI gives you sort of the minimal kind of thing, right? It's data layout, et cetera. But Rust is such a rich language. When we specify an ABI for Rust, could we say that the ABI also captures all the things that a type specifies, including ownership and borrowing? That would be a rich ABI. If you could specify all of those constraints, then when you link with other code at that target level, you know what needs to be owned, et cetera, and the other code needs to show that it satisfies the ABI. So that means that all those ownership and borrowing invariants need to be respected. But in order to do that, we kind of need to get the information that's in the high-level types and say how, construct models of it to say that this is true even of the target code, right? And these kinds of relations can let us do that. So richer ABIs, basically, for languages that have much richer types, right? We shouldn't just keep resorting to the lowest common denominator C for absolutely everything, which is what happens in the ABI world, in the sort of linking interop ABI world right now. Everyone just sort of resorts to the C ABI because it's the lowest common denominator, not very rich. So can we start to do research on like richer ABIs and see what benefits that gives us? And basically, this would then allow you to prove that any compiler you build is ABI compliant, given an ABI for the language, whatever your language might be. It can allow you to prove that as you evolve libraries over time, that they remain ABI compliant, that they are ABI compliant to begin with, and that they remain ABI compliant. So it's a lot of stuff that can be verified if you have an actual formal spec in place. So we've done, to illustrate the idea that these realizability relations are useful for specifying ABIs, we've done a case study with a functional language with a reference counting implementation, very much inspired by Swift. And kind of investigated various, Swift is very cool when it comes to thinking about the philosophy of evolvable ABIs. So we tried to sort of examine some of those decisions. And what we want to work on next and have sort of started on is basically a Rust ABI, but just to the WebAssembly platform for now. Ultimately, you want to go to lower levels, but one step at a time. Going too low level is a lot of subtlety and technical detail. All right. So you've heard about logical relations. Hopefully, I've given you a flavor for the very, very wide array of things you can do with them. And I hope that it serves as a good foundation for any future work that you're trying to do. And if you have interesting problems that you're stuck on or something, I'd be happy to talk. All right.